Earth is born out of chaos and catastrophe. Despite such hostile conditions, life emerges on our planet. But it must withstand deadly disasters again and again. Planet Earth is a wild world, shaken by unimaginable impacts. Volcanic eruptions that flood the landscape, and drastic climate changes that lead to ice ages that freeze the world from pole to pole. Yet each assault creates a path for something new. Life always finds a way, despite being constantly put to the test. Without these catastrophes, life as we know it would not exist on our fateful planet. Chile. In the heart of the Atacama Desert, scientists are trying to understand how our home, planet Earth, came into being.
Astronomers are like archaeologists, so we have somehow to reconstruct the past.
Professor Thomas Henning is one of the world's leading experts on planet formation.
We live in a period of discoveries, and it's really absolutely exciting to be part of this and to be part of this great adventure to unravel the mysteries of the universe.
As the end of the last century came to a close, a staggering discovery was made. Scientists had measured the slightly shifting light of a star. From the data, they could tell that a giant object had to be pulling on it, a planet. This was the first planet outside our own solar system to be discovered, a so-called exoplanet.
It was an absolute game changer. I think it was one of the most fundamental discoveries. And since that time, we can put our solar system in context.
This newly found planet is far from unique. Scientists believe that in just our galaxy alone, there are around 100 billion planets. Many could even foster life. By researching these distant planets, scientists hope that they can shed more light on our own planet and its formation. But detecting them remains a challenge.
One of the techniques is actually using a dip in the light intensity. So let's imagine that the lamp would be the star and this would be the planet. Then we would see a slight dip in the light intensity, and we could conclude that a planet crossed the stellar surface.
These so-called transits can help determine a variety of different exoplanet characteristics, from the size of the exoplanet's orbit to the radius of the planet itself, even its atmosphere. But there is one thing this method does not provide.
Our ultimate goal is to image planets, and that is actually really, really difficult. And the reason for that is that the central stellar object is overshining the planet.
To image distant exoplanets, Professor Henning works at a high-tech facility, the European Southern Observatory at Mount Paraná. Located in the Atacama Desert in northern Chile, the astronomical observatory towers above the desert. By analyzing exoplanets and their systems, scientists can find out how our solar system and planet Earth have formed. And they also try to discover if there is life in outer space.
This is a magic place. The landscape is just breathtaking. It's one of the greatest places for astronomy. We have many clear nights and we have very little water in the atmosphere. It's very dry, and that's great for observing stars and planets.
For this reason, a special array of telescopes is utilized here to help scientists understand the birth of our own planet. It is called the VLT, or Very Large Telescope. Each of the four 27-feet telescopes can take pictures of tiny celestial objects over 4 billion times fainter than what can be seen with the naked eye. But even this is not enough. Beneath the telescopes, a collection of high-tech systems enables the scientists to create a virtual mega telescope.
We are not only using a single telescope, but we are combining 4 of the big telescopes, and that provides us with a spatial resolution of a 140-meter telescope.
With their equipment, the scientists can now not only detect, but image planets. When the sun sets, the magic begins. Laser beams are used to create artificial guide stars to correct the distortions caused by the Earth's atmosphere. In the night skies, the scientists are looking out for exoplanets, especially newborn ones, as they might deliver important clues to understand how planets form. In the control room, Thomas Henning and his colleague are monitoring the telescope's measurements.
So, Conrad, I think the telescope is ready to go. Okay, let's get started.
At a distance of nearly 400 light years, the astronomers have identified a young star. In its vicinity, they are now trying to capture an image of an exoplanet. To do this, Thomas Henning is using a stellar coronagraph, an instrument that emulates a solar eclipse. It blocks out the bright direct light from the star so that nearby planets become visible. In 2018, the scientists finally succeeded in capturing an amazing image.
For the first time, we could see a planetary system in its birth environment. So we could practically study a baby planet. And this was a very emotional moment because I tried that for many years.
The picture revealed a disk filled with gas and dust surrounding the infant planet, leftover material from the formation of the system star. From the image, Professor Henning could tell that the baby planet was a gas giant, at least 5 times the mass of Jupiter, the largest planet in our solar system.
We could analyze its atmosphere, and everything points to an atmosphere which is very dusty, which actually has clouds, so it must be something similar to the desert here when we have wind.
The picture also tells Professor Henning something about the dramatic past of the exoplanet and its system. Because of its massive gravity, the planet sucks in everything in its path, forcing the region around its orbit to become devoid of gas and dust. The exoplanet shifts its orbit towards its star, sucking in even more material on its way. Any smaller objects it comes across are simply consumed, even other planets.
We see this black stuff here, and this is caused by the fact that these giant planets clean everything. So there is no other planets in a catastrophic way. They remove all the material from the disk.
Since the detection of the first exoplanet, thousands of them have now been found in our own galaxy alone. By witnessing the birth of a planet for the first time in history, Professor Henning and his team have gathered important data.
Our exoplanet research now paves the way to answer 3 of the most fundamental questions mankind can ask. First, are we actually alone in the universe? Is there life somewhere else? Second, how did life actually form in the early history of Earth? And the third question we can also ask and answer, how did Earth form and how did our planetary system came about?
It is still miraculous how our planet has grown from stardust to a place fit for life. But the latest scientific discoveries have shed more and more light on how this could have happened. The formation of our world and the emergence of life are mysteries that scientists are trying to solve. Laura Kreitberg from the Max Planck Institute for Astronomy in Germany is passionate about finding these answers. Since her childhood, she has been fascinated by the vastness of the cosmos.
One of the things I asked my mom when I was very young was, where is the edge of the universe? And she didn't know the answer, but I've been asking these questions ever since.
For me, looking in the night sky really puts our life on Earth in context. We know now that almost every other star in the sky has at least one planet. And when you get to see all of them up there twinkling at us, you can imagine that perhaps there's an Earth-like planet with people on it wondering about us just the way we would wonder about them.
Whether we are alone is still unclear. But how our Earth evolved into the place it is today is only just beginning to be unraveled. The exploration of our solar system brings researchers one step closer to solving this mystery. To understand how our home, a small rocky planet, third from the sun, became a place fit for life, we need to go back in time, to the beginning, over 4.5 billion years ago. Scientists believe that our solar system begins as a vast interstellar cloud of gas and dust, twisting through the universe without direction. Eventually, the cloud collapses in on itself, after becoming gravitationally unstable, forming a solar nebula, a spinning, swirling disk of material.
And what tends to happen is that whatever random motions existed at the beginning, those are preserved, so you hold on to the rotation. But the up and down motion cancels out. Material moving down collides with material moving up. And so that flattens the disk over time, and you're left with this rotating flat disk that the planets form in.
At the center of the disk, gravity pulls everything inward.
The material at the center got hotter and hotter and higher pressure, and eventually reached a point where the density and the temperature and the pressure were so high that hydrogen began to fuse in the core.
With the pressure in the core so immense, hydrogen atoms begin to combine and form helium, releasing a tremendous amount of energy.
This is some of the most dramatic events in the history of a solar system.
With that, our sun is born. A shining mass of chemical elements forging light into the vast darkness. The temperature in the core of the sun reaches more than 27 million degrees Fahrenheit, driven by internal nuclear reactions. It's been estimated every second the sun produces more energy than 1 billion atomic bombs.
The sun accreted almost all of the gas surrounding it. 99% of the material went into the sun, but there was a little bit left over that formed a little protoplanetary disk. We call it a swirling cloud of gas and dust around the young star, and that's where the planets were born.
The little material that remained around the heart of the new star was enough to form the raw ingredients for a new system of planets orbiting around the sun. But how this material turned into planets has always been a subject of debate.
One of the newest ideas about how planets form is called pebble accretion. And with this idea, the planets are growing out of small pebbles, so a little bit at a time.
Within the giant disk of gas and dust that circled the young star, particles smaller than the width of a human hair started to clump together and coalesce. By this, they grew into larger and larger pebbles, which started to collide with each other. It's a process that can be compared to colliding bumper cars at the amusement park.
In the young solar system, there was a lot of material that was bumping into each other, exactly like these bumper cars are bumping into each other. But eventually, with bumper cars, you bump and you separate. But when planets form, the material is actually able to stick together and grow to form the planets we see today. Just like when the bumper cars come together and the one in the middle can't escape.
From these collisions, pebbles eventually grew into gigantic bodies of rock, some the size of the biggest asteroids we find in the solar system today. Eventually, some of these objects became large enough to take on a spherical shape, under the influence of their own gravity. At this stage, these protoplanets started to grow faster and faster by consuming all the material in their orbit around the Sun.
And these pebbles are able to be vacuumed into the young growing planet very, very quickly, very efficiently, so that we can grow very large planets on the short timescales that we observe around other stars.
Growing planets is not unlike making cotton candy.
And now, watching this cotton candy slowly grow up into a big ball is almost exactly the same as a protoplanet accreting more and more gas and dust as it moves through the protoplanetary disk. As it moves through its orbit, you can see it growing larger and larger and larger until at the very end, you have a giant planet, or perhaps cotton candy. Dankeschön.
The newly born planets are anchored by the gravity of the Sun, which they orbit in various paths. It is this gravity that keeps these protoplanets from flying off into the universe or collapsing together. In the outer solar system, our biggest planets are formed. They absorb all the gas within the protoplanetary disk, becoming the gas giants, Jupiter and Saturn, and the faraway ice giants, Uranus and Neptune. Without any gas left in the disk, the protoplanets in the inner solar system remain rocky and relatively small, becoming terrestrial planets like Mercury, closest to the Sun, Venus, and Mars.
We think that planet formation happens pretty quickly. So after the star forms and there's this disk of material around it, after not even 10 million years, the planets can be fully formed after that. And that's just the blink of an eye in the length of the solar system.
One of those planets has formed between Venus and Mars, Earth. Born from tiny dust particles like its cousins. But it's not the blue planet we know today. Earth is a spinning mass of red-hot rock. Our barren planet looks like it could not contain anything related to life.
The Earth, during its very early lifetime, was not a friendly place for life at all. Imagine yourself standing on top of the early Earth just after it formed. This is not a happy place to be. It is excruciatingly hot. The surface is so hot that it's molten lava. You would not survive very long. But that is not your only problem.
4.5 billion years ago, the solar system was vastly different from what it is today.
Not only was the young Earth extremely hot, extremely inhospitable to life as we know it, but it was about to face a very enormous challenge.
A catastrophic event was about to take place that would change the history of Earth forever. It is the moon that provides us with evidence of this first catastrophe. In 1969, the Apollo 11 mission brought back the first moon rock samples to Earth. Since then, NASA has retrieved thousands of samples on their missions. Because the moon, unlike our Earth, hasn't changed as much since its formation, these samples can help unravel how the past has shaped our present, holding the key to the mysteries of the emergence of the moon and the Earth alike. Zurich, Switzerland. Every year, NASA distributes some of their moon samples to a select group of scientists around the world. Professor Maria Schönbechler at the Swiss Federal Institute of Technology is one of those recipients.
They are much more valuable than gold, so a gram like that is about 10 or 20 times more valuable. The lunar surface is very old and has hardly changed compared to the Earth, and that helps us decipher the secrets of the early Earth and the early Moon. The Moon is like a window back into the past, and I find that fascinating.
Professor Schönbechler is looking for particular chemical signatures in the lunar rocks that might reveal clues about their origins. In an experiment, she now wants to compare the composition of the Moon to the composition of Earth.
Here we have a dissolved sample of the Moon, and this is an Earth sample from Hawaii. Now we can analyze these and see how closely related Earth and Moon are.
Using isotope analysis, Maria can compare the samples on an atomic level. She is particularly struck by the composition of the respective chromium isotopes. The measured values are astounding.
What we see here are the measurements from the Earth sample and the Moon sample. All the bars are identical. That means the Earth and the Moon have exactly the same fingerprint. And that in turn tells us they must be very closely related. So the Earth and the Moon are geological twins. The question now is, how did that come about?
There are multiple theories about how the Moon was formed. The results of the analysis suggest that its formation is closely linked to the history of Earth.
People have wondered for a really long time how Earth's moon formed, and there have been a lot of different ideas how it happened. One of them was that the moon actually was a little piece of the Earth that got broken off early in the lifetime of the planet. Another idea was that the Earth and Moon actually formed at the same time from the protoplanetary disk, like a little binary system. But the theory that has the most support now is actually much more spectacular.
4.5 billion years ago, planetary embryos were circling around the Sun, together with a countless number of smaller but still huge chunks of rocks. The early solar system was a hazardous place. Maria Schönbechler can read this in the Moon's surface.
The exciting thing about the Moon is that its surface is very old. That means if we study the Moon, we also study the history of the Earth, because it's a mirror image. And if we now look at the surface of the Moon and see all these craters, some of which are also extremely old, then we know that early Earth also suffered many impacts, from asteroids or comets, just like the Moon.
Just after the planets formed, the solar system was a very dangerous place to be. There was material left over from planet formation that was flying around. Collisions were common, and the Earth was about to experience one of the most catastrophic collisions in its entire history.
In the early days of our solar system, Earth was being bombarded.
The young solar system was a very violent place, and collisions were common.
But the most apocalyptic collision in the history of our Earth was about to take place. At this time, Earth was an ocean of molten lava, hundreds of miles in depth, perpetually stirred up by the impacts of asteroids and comets. It had nearly reached its final size. But approaching from the dark void was Theia, a massive protoplanet the size of Mars. Like Earth, it had been growing quickly by consuming everything in its path. And now, it was heading straight for Earth. The impact of Theia nearly destroyed Earth. Vaporized chunks of our young planet's crust were thrown into space.
The scale of this impact is hard to even imagine. It was 100 million times larger than the impactor that we think killed the dinosaurs. The impact was so strong that Thea was obliterated, and what was left over was chunks of both Thea and the surface of the Earth that were ejected into orbit around Earth itself and were held in by Earth's gravity. That debris cloud flattened into a disk not so different from the original disk around the young sun where the first planets formed. As material orbited around the young Earth, you had small pebbles, small grains bumping into each other that grew and grew.
Gas, dust, and rock coalesced into a spherical shape that continued to orbit Earth. A new world was created, the Moon. But it was far from the one we know today. Right after its formation, the Moon was about 17 times closer to our planet than it is today. Its proximity to Earth had dire consequences, bringing violent instability to the molten planet it orbited. Earth had passed its baptism of fire. But even a long time after the impact, our planet was far from being a place where life could emerge. How this happened is one of the key questions that scientists at the Max Planck Institute for Solar System Research in Göttingen, Germany, want to answer. One of them is Dr. Fred Gossman. He participated in the European Space Agency's Rosetta mission, where a probe was sent to a comet to look for earliest traces of life in our solar system.
People came up with the idea in Europe, let's fly to a comet. Let's not just fly past it, let's go to the comet, orbit it, land on it, and see what it's made of. And so the question is, did comets bring something which helped for life to emerge on Earth?
The comet, known as 67P Churyumov-Gerasimenko, was on an elliptical journey, stretching between Jupiter at one end and the region between Earth and Mars at the other. The plan was for the Rosetta probe to travel with the comet before dispatching a lander to the comet's surface to collect invaluable data. Fred Gossman developed a special instrument for Rosetta's lander, Philae, that's capable of measuring the properties of the comet.
Philae is a little bit of a small beast landing on a comet, and it has eyes, which are the camera. It's got a sense of feeling, which is the feet, and this thing was the nose. It is a chemical instrument. It's sniffing for molecules and identifying them by technical means.
In 2004, the Rosetta probe was launched on its billion-kilometer journey. After a flight of 10 years, the spacecraft finally reached its destination. The optical instruments on board Rosetta catched a glimpse of the strange-looking comet.
And it slowly grew in size, and then you saw, oh no, it looks like a rubber duck. And it was pretty clear, don't call it a duck.
Rosetta entered the orbit of Comet 67P. Then, Philae was released to land on the surface.
The landing itself was really exciting. We saw images of the camera system of the orbiter that the legs had unfolded. It worked. The legs were nicely spread out, and so the thing came down, and then we heard touchdown. We are on ground. People at ESA were cheering and everything, and then the engineers scratched their heads and said, no, it's moving. And that was really frightening.
The landing gear did not appear to be working as planned.
What we have here is one of the three landing legs. So in order to stay on the cometary surface, which we already knew would be very difficult, we gave this lander harpoons, claws, teeth, everything. And this is one of the feet. When these paws touch the surface and they experience a force, are being pushed back, they could retract and push forward. We call it an ice screw. The idea was, well, you touch the surface and you recognize that by some motion in the mechanical system. And once that happened, you fire harpoons into the comet and then you secure everything, you pull the rope of the harpoon and everything. Nope.
The harpoons that should anchor Philae to the landing spot failed. Untethered, Philae bounced off the comet for the next 2 hours. Finally, the lander settled in the shadow of a cliff.
The final position where it came to rest was so awkward. It wasn't standing on its legs, it was kind of upway. One leg was really pointing upwards. The drill was kind of poking into nowhere. It didn't reach the ground. So it did all its motions, but it didn't give us a sample because it couldn't touch anything.
It seemed that the billion-dollar mission to find out more about the origin of life had failed. But despite things not going to plan, samples were taken.
We were a bit fortunate because we hit the ground and obviously stuff was excavated and there was a plume of something coming up. And this very initial measurement, where we just switch on the mass spectrometer, see what the environment tells us, only these 2 tiny minutes of measurements gave us a brilliant spectrum. For me, when I was seeing it, it was the most sexy mass spectrum in the world. And it still is.
After a thorough analysis of the measurements, the comet's properties were revealed. It contained carbon, hydrogen, oxygen, nitrogen, and even more.
We found molecules, organic molecules, and if you put them in the right environment, they would be suitable to combine and to build anything you need in order to have life. I would say that if you have a planet and many comets fall onto it and they are of such composition, it would create an environment which life would be happy to thrive on.
Whether it was really comets that started life on Earth is debated. But even if they did deliver the building blocks, our planet needed a radical change to enable life to evolve. There was still another ingredient that was missing: water. Comets like 67P originate from beyond the orbit of Neptune, or even farther out, and are supposed to carry a lot of water in the form of ice. Many scientists therefore believe that comets also brought water to Earth. High-resolution images of Comet 67P indeed show the presence of water ice on the surface. But the analysis of the atomic makeup of the comet water shows that it is different from the water we have on Earth. This means that water on Earth cannot have been delivered by comets. It must have come from somewhere else. On September 12, 2019, more than 500 people along the North Sea coast reported seeing a strange phenomenon across the sky in broad daylight. While filming a selfie video, a kite surfer from northern Germany captured the event in the background, a flash of bright light. It was a meteorite on its way down to Earth. Professor Thorsten Kleine, director of the Max Planck Institute for Solar System Research, wants to find out if this piece of rock can help solve the riddle of water.
A day after the flash, a 25-gram piece of a meteorite has been found near Flensburg in Germany. It would have looked just like this, a black rock, not very spectacular looking, but scientifically extremely interesting.
The analysis shows that the meteorite is nearly as old as the solar system, and that it is a piece from an asteroid. While comets are icy with tails and come from the outer solar system, asteroids are rocky and mainly stay in a belt between Mars and Jupiter. Because of their relative proximity to the Sun, they usually do not consist of ice. Nevertheless, the analysis in the lab shows Thorsten Kleine that they do carry a precious cargo.
If we look into this, we can find hydrogen and oxygen, the building blocks of water, bound into minerals. But most importantly, we can also find the signature is the same as it is for water from the Earth. That means that the water on our planet might have come from asteroids.
Further research also revealed that mineral-bound water-containing asteroids initially came together to form our planet. This means water could have been on Earth from the beginning, albeit not in liquid form. But how did the mineral-bound water transform the hellish early Earth into something that could host life one day? Over millions of years, the hot molten planet cooled enough to form a crust. The heat below the surface released, amongst others, oxygen and hydrogen that was bound in the minerals. The outgassing formed an atmosphere. Water vapor condensed and fell onto the rocky planet as rain. It rained for millions of years, long enough to create the first oceans. The world that had once been a ball of fire had become a world of water. 200 million years after its formation, Earth is covered with liquid water. But despite this, there is no life yet, because our planet is still a hostile place. One reason for this is our moon. The impact of Theia has caused Earth to become bound to a new moon, and this is causing havoc. Over 4 billion years ago, the moon was very different to what it is today.
Just after the moon formed, it was much closer to the Earth than the moon is today, more than 10 times closer, so it would have appeared very large in the sky. And not only that, but it would still be incredibly hot from the violent impact that formed it, and so it would be glowing. You'd be able to see it even during the daytime.
With an object this large and this close to Earth, cataclysmic effects shook our planet.
The most important force that governs the motion of the Earth and moon is gravity. The Earth is exerting a gravitational pull on the moon and vice versa. Similarly, when you're on a carousel and you're moving quickly around the center, there's a centrifugal force that is pushing you outwards, and that's the exact same force that would be at play with the Earth and the moon.
The moon tore at our young planet's surface.
This was a very dramatic environment for the early Earth. The moon's tidal forces were driving enormous waves in Earth's ocean, so every wave crashing on the shore would have been like a tsunami at that time.
The world of water was shaken by the enormous force the moon exerted.
The Earth during its early lifetime experienced some very tumultuous years. So you can think of the Earth kind of as a teenager early on in its life.
Not only the proximity to the moon was causing havoc at this time, Earth itself was also spinning up to 6 times faster around its axis than it is today. It was a wild planet.
Just after the moon was formed, the Earth was spinning very, very fast. The length of the day was only about 4 hours.
Earth was far from the hospitable world we have today, but this was about to change. The moon, the very thing that was causing so much stress, was also about to help Earth take a vital step towards life.
The moon was tugging on the Earth so strongly, it actually caused something called tidal friction, which caused energy to be lost from the early Earth-Moon system.
Due to the fact that the moon tugs at our planet, the tides were created. Huge waves bulge out and exert a gravitational pull on their own on the moon. Because it takes time for all that water to shift and pile up, the bulging oceans don't exactly match up with the position of the moon. They're always a little out of sync. This creates friction that slows Earth's own rotation, albeit very slowly. Every 50,000 years, the days become 1 second longer. This also creates forces that change the moon's orbital speed, causing it to slowly fall away into space.
Today, the moon is still moving away from the Earth, little bit by little bit, about 4 centimeters per year. As the moon moves away, the gravitational pull is a little bit less, and that allows the Earth's rotation to slow down just a tiny bit. As this happens, the moon will slowly move away. The amount of friction decreases, leaving the Earth in a much more placid and calm place for the origin of life.
As time passed and the moon continued to move away, our days gradually got longer, and Earth's rotation got slower and slower. The new moon finally brought stability to our planet, setting the stage for life to begin. At the Ludwig Maximilians University in Munich, Germany, scientists want to find out how life might have evolved on early Earth. For Professor Oliver Trapp, chemistry is the key to life.
You can create new molecules, you can create new functionality, and you can make absolutely new matter which didn't exist before. And this was already fascinating me as a child.
In his laboratory, Professor Trapp wants to understand how life formed over 4.3 billion years ago.
My goal of this research is that we discover a mechanism which led to evolution.
Oliver Trapp wants to form life in a test tube.
We tried to simulate the processes which took place on the early Earth.
Trapp's work is based on a groundbreaking experiment. In 1953, biologist and chemist Stanley Miller and his mentor Harold Urey built a setup that tries to show that life emerged from a primordial soup. They injected ammonia, methane, and water vapor into an enclosed glass container to simulate what were then believed to be the conditions of Earth's early atmosphere. Finally, Miller and Urey also replicated lightning strikes.
They induced a reaction by making sparks. And the amazing outcome was that they observed the formation of amino acids.
Amino acids are the molecules that combine to form proteins and are the building blocks of life on Earth. The experiment laid the foundation to further research on the origin of life. But Miller and Urey made one mistake.
What they didn't know at this time was the composition of the atmosphere. They assumed that we had an atmosphere with methane gas. And it turned out in the 90s that this was wrong.
Professor Trapp now wants to repeat this experiment, but this time he's incorporating the latest understanding of the composition of ancient planet Earth. The starting ingredients is the inorganic matter that was available on early Earth.
So we are starting really from very, very simple molecules. We had carbon dioxide in the atmosphere. We had water, also as vapor, as steam in the air, and of course nitrogen.
But Oliver Trapp also adds a dissolved meteorite to the mix to duplicate the bombardments that took place on early Earth. By this, he creates simple organic molecules. Now, Professor Trapp puts this primordial soup into a container, together with water, which is heated to induce evaporation, replicating the water cycle as it may have been 4 billion years ago. Then comes the final important step of the experiment.
This is a Tesla coil which generates sparks, and this simulates day and night cycles, which is very important to have the energy from the sun in our reaction setup, and I expect that this will trigger new reactions and provide new material.
1 million volts ionize the air and generate lightning. Each flash replicates a day on which the sun supplies our young planet with energy. By doing so, Professor Trapp simulates years of evolution.
This actually doesn't look like much. It looks like water, but if the experiment worked, we will have the first building blocks of life.
The molecules are much too small for the eye to see. Using a gas chromatograph, Professor Trapp can find out what has formed in his primordial soup.
This is adenosine, cytosine, and guanosine, and these are the DNA building blocks. So far, we have not formed life, but I'm pretty sure that with this, we can continue and we will see the formation of life in a test tube starting from inorganic material.
It is these compounds which would eventually kickstart the evolution of life on Earth. Over millions of years, these building blocks would replicate and assemble into cell membranes, until eventually a single-celled organism emerged. This organism, which lived around 4 billion years ago, would become known as LUCA. our last universal common ancestor. But where on Earth did life begin? One possibility is the deep sea around hydrothermal vents. Chimneys formed where seawater comes into contact with magma on the ocean floor, resulting in streams of superheated plumes. But life may as well have formed in scalding, highly acidic hot springs environments, like those found today in the Yellowstone National Park. Eventually, the organism's ancestors will make the first step outside of water. How and why this happened is only just being revealed. But what is clear already is that our hostile Earth plays the central role in the evolution of life. One of the best places to understand just how hostile our early planet was can be found right here on Earth today. The Atacama is one of the driest deserts in the world. Here, a team of German biologists try to trace the ways in which early life evolved. And they want to find out how life was able to gain a foothold outside of water.
Michael. Hi, it's Luis. Nice to meet you.
Nice to meet you. Hi, I'm Patrick. Nice to meet you.
I'm Luis. Nice to meet you.
Hello.
The Panda Azucar National Park is part of the Atacama Desert. Within the park, there is supposed to be an area which is particularly hostile to life, a place that is closed to the public. The deeper Patrick Young and Michael Lakatos venture into the desert, the more barren the landscape becomes. Here it is so dry that seemingly nothing grows anymore, the perfect place to search for life. On the desert floor, a dark crust is the only unusual thing they discover.
Can you imagine what that might be?
It's mineral.
Do you really think so?
Yes, those are black pebbles here.
Closer analysis of the desert floor amazes the scientists. Tiny dark cracks run through the pebbles. For the experts, this is a possible sign of biological activity.
I have another idea. You got that water bottle?
The scientists know that this rock does not absorb water. If it does, this would be a clear sign that it has been penetrated by an organism.
You see how it changes?
Oh yeah.
Now let's give it a moment. I'm going to look through there again, but I think I can see it turning green.
A change in color would also indicate the presence of an organism in the stone.
We just found out that these are microorganisms that are sitting on these little pebbles. And now we have to take our instruments to find out what they are doing here, how they can survive, and what kind of microorganisms they are.
The scientists want to find out whether these microorganisms are actually alive. For this, they are using a measuring device that is capable of detecting photosynthetic activity. First, they measure the dry rock. The red color of the display means no activity.
So hold on, I sprinkle it with water now. You can start the measurement.
Yeah.
That's amazing. It's alive.
We found out that there's a color change of the photosynthetic signal. That is, it flips from red to green and blue. And that shows us we actually have photosynthetic activity here, and therefore life.
With a field microscope, the scientists now want to find out which organisms have been able to survive in this hostile environment.
Michael, come here and take a look at this. When I adjust the focus, you can see that there is a lichen. So you can see the fungal structures, and here the green algae. And also here, it's everywhere.
That's really beautiful.
Lichens are symbiotic microorganisms that exist on Earth for about 400 million years. In this case, they consist of an algae and a fungus.
The algae is photosynthetically active, so it converts light, CO2 from the air, and water into sugars. And these sugars can be taken up by the fungus partner. It feeds on them. And in return, the fungus partner positions the algae in the lichen in an optimal position in the organism that is formed, so that the algae can optimally photosynthesize. Only through this symbiosis can these individual partners survive here together in the Atacama Desert.
But from where does the organism in this area get the vital water?
We are in one of the driest and oldest deserts on Earth, but still we are only about 12 kilometers from the coast, that is, over here. Water vapor rises there, condenses out as fog, and then moves very flat across the landscape. That's a super small amount of water input, but that amount is enough to make life possible here.
With a drone, the scientists now want to get an overview of the distribution of these organisms.
Yeah, go up a little bit more. Right. Now if you go to the left another bit.
Gradually, the full extent of the growth is revealed.
Look at this. It's really everywhere.
Patrick Jung and Michael Lakatos suspect that the lichens here form a superorganism, comparable to a coral reef that covers large parts of the hostile Atacama Desert.
The microorganisms that we found here are adapted to extreme locations. By working together, they have made this leap into the landscape. And that's a comparable situation to what we find in the early history of the Earth. Through these abilities, out of the corporation and symbiosis of adapted microorganisms, life that originated in water might have leaped on land.
After almost 4 billion years, life has developed innumerable characteristics and forms. In the course of evolution, highly complex living beings have developed. But the road to the diversity we have today is a long and rocky one that puts life to the test again and again. However, one thing is for sure. Without catastrophes like the apocalyptic collision with Thea, life on Earth, as we know it today, would not exist.